So last time we were last time we were in the middle of um, heavy slogging through working out the word identity following from the symmetry that we derived and understanding it as a soft theorem. And we're going to get back to that in a second. But I want to, so this is a subject which is sort of, there's a crisscross of connections between different things. And I've chosen one path through it. There would be many other paths that one could take. But from time to time, I want to allude to, I'm going to take a little intercession here, and I'm going to allude to some relationships to some other subjects, which we will cover in more detail later on. And one of the big things is that there's a parallel story. I could have essentially given every lecture talking about gravity instead of talking about electromagnetism. And even though electromagnetism is simpler than gravity, there's fewer indices, oddly, a lot of the concepts that we talk about are sort of more familiar in gravity than in electromagnetism. So I'm going to talk about two things. I'm just going to say a few words about the gravity analogs of what we've been discussing. We'll get to them in detail later. And then I'm also going to say some things about how the symmetries that we talk about, the large gauge symmetries, can also be thought of in the framework of a field known as the study of asymptotic symmetries. So let me talk about the gravity analog. So in gravity, if you look near past or future null infinity, the metric has an expansion, 1 minus the so-called Bondi mass aspect, which was introduced in the early 60s by Bondi. And this Bondi mass aspect plays a role in gravity, similar to the role played by the electric field in electrodynamics. And indeed, it turns out that it is antipodally identified, just as the electric field was in electromagnetism, at the past boundaries of Scry. And one can therefore define a charge, Q plus F is equal to 1 over 4 pi times Newton's constant. The integral, Scry plus minus d squared z, gamma z bar, times convoluted with any function f. This is the analog of the function epsilon, and then the Bondi mass aspect. And that is equal to the same thing, which is just like this, except we'd be integrating over Scry minus plus. And so this gives us an infinite number of conservation laws in general relativity, or in general relativity coupled to anything, basically any theory of gravity. And then you can go through exactly, and we'll do pieces of this, exactly the same procedure. There's a symplectic form for gravity, and so which was worked out in the 70s and 80s. And you can push it up to Scry, or up to Scry plus, or down to Scry minus. You can compute the commutators. You can ask what this charge generates using the constraint, and then you use the constraint equations of general relativity to write this as the surface integrals over scri plus or scri minus. And you find that it generates a diffeomorphism under which the retarded time at infinity is shifted by an arbitrary function of z. So there's a picture like this. We have a sphere up at null infinity, and we shift it in a way which doesn't depend on the retarded time at u. We translate it in a way that doesn't depend on the retarded time at u, but depends on the angle on the sphere. Now, this all makes perfect sense, and these are known as super translations. And this all makes perfect sense. If we look at the case where f is a constant, the integral of this is just the total mass, which is the Hamiltonian. It's the total energy of the system, the Hamiltonian. And we know that the Hamiltonian should generate, via commutators, time translations. And indeed, we see that in that case, it is just generating a constant shift in time. So, but what the new thing is that the symmetry of general relativity is not just the symmetry under constant time translations, but we can have time translations that vary over the angle of the sphere. And this is just like what we've been discussing in electromagnetism, except instead of time transformations in electromagnetism, we had gauge transformations which depended on the angle on the sphere. And now, the funny thing is that but there's some similarities, but there's some interesting differences. Because in these, a gauge transformation, a phase on a state, in classical electromagnetism, the phases are unobservable. So in order to talk about measurements of these, in order to talk about observable consequences of these angle-dependent gauge transformation, we have to talk about quantum interference. And here, because these gauge transformations leave what are usually considered the observables in electromagnetism, like the field strength invariant. But here we have an actual physical time translation. So if we start moving things around, translating them forward or backward at time in an angle-dependent way on the sphere, that is something which has a classically observable consequence. So these super translations were understood. They weren't really understood to be a symmetry the way we understand them now, but pieces of this super translation story were understood already 50 years ago. And so it's kind of odd that this symmetry of gravity was at least partially understood 50 years ago, whereas the fact that there are these symmetries in electromagnetism was only understood in this language in the last few years. All right, now, so that's we'll discuss this more later, but that's the gravity analog of what, in 3 minutes, of what we've spent 3 lectures on. Are there any questions about that?
What are super rotations?
Right. So the super rotations, so this subject sprawls out in so many different directions. There are more symmetries in electromagnetism than what I've told you about. There are more soft theorems. There are more symmetries. And I'm going to tell you about them later, but I can only do one thing at a time. And the superrotations are gravitational analogs of something we have not yet discussed in electromagnetism.
But you can't just simply modify the Hahn function so it depends on the rules.
No, it's more subtle than that. Yeah. Okay. So now let me talk about asymptotic symmetries. So asymptotic symmetries, I like to say that this subject is more of an art than a science, but it's been in, the rules keep changing. However, despite the fact that it's not a very this way of thinking about things is not very rigorous, it's been extraordinarily fruitful. It's been a shortcut to a lot of really important physical insights, and indeed it is the way that what I just told you, that it's the way, this way of thinking about things is how the symmetries in electromagnetism were first uncovered. And then once you get an idea of how it should go, then you can go and try to find more rigorous methods. So, you know, the fact that it's an art, not a science, is not a derogatory statement. In fact, maybe art is better than science. You know? So what is, so there's something called an asymptotic symmetry group. And it's defined as the allowed gauge or local symmetries divided by the trivial gauge or local symmetries. And I think the first application of this was, so you have some local symmetry group. It's most often been used with diffeomorphisms, which I'm concluding under the rubric of gauge symmetries. And you have some, you're studying the theory on some space-time, and you have some boundary conditions that tell you what your field components, how they should behave near the boundary. And the allowed gauge symmetries are any ones that respect the boundary conditions. And the trivial gauge symmetries are the ones that act trivially on the physical data of the theory. Now, both of those, the top and the bottom, are a little bit squishy, because how do you decide what you're going to allow, what kind of behavior you're going to allow at infinity? And in some cases, there are sort of known cases in which, in many cases, in fact, the theory depends on, part of the definition of the theory is specifying what those boundary conditions are. And then how do you decide what is and isn't trivial? One way to do that, but it's not always done this way, is to construct some kind of charges, but in practice that's often extremely difficult to do. And then if the charges vanish, you might say they're trivial, but that also turns out not to always be exactly right. But despite the ill definition of this, it's been extraordinarily useful. So the first application of it, I would say, was by Arnowit, Deser, and Misner, who were considering asymptotically flat. They wanted to recover the Poincare group, so out of general relativity. So it seemed intuitively obvious that if you had an isolated system that was flat at infinity, that such systems should be flat as you go to spatial infinity, that such systems should be acted on non-trivially by the Poincare group. In other words, if you have a black hole, an asymptotically flat black hole, and you boost it, that is a diffeomorphism. It should certainly be allowed, but it's not trivial. You change the energy. Similarly, if you translate it, it's in a different place. So, so they indeed showed that. So they put some boundary conditions. They gave a definition of when a space-time was asymptotically flat spatially, and figured out what the allowed diffeomorphisms were, and then they showed that there were that the asymptotic symmetry group, its spatial infinity, acting on the space of asymptotically flat initial data, which they took to be the phase space, was just equal to the Poincare group. Another famous application of this was in ADS3 in the late 80s, Brown and Henault, and they really, Arnowit, Deser, and Misner found something that everybody was expecting. Brown and Henault found something that nobody was expecting, which also shows the power of the method. It's not just a way of confirming what you already know. They found that if you take three-dimensional anti-de Sitter space, and how did they decide? They put some boundary conditions on there, and they wanted to put the boundary conditions so that you could have, it was already known that there were black holes in three-dimensional anti-de Sitter space. They wanted to have weak enough boundary conditions so that you could allow all the black hole solutions. And so they made them just weak enough to allow that. And then they constructed some charges, and they found that in that case the asymptotic symmetry group were two copies of the Virasoro group, and actually from their construction of charges, they were actually able to compute the central charges of that asymptotic symmetry group, and that was a really, impressive demonstration of the power of this way of thinking about things if you manage in making the right guesses, which sometimes is not so hard. Okay, so what would we expect in gauge theory? Well, just in electrodynamics. Well, in three-dimensional anti-de Sitter space, the boundary is time-like. So things can bounce off the boundary. So you might think, and indeed it does happen in three-dimensional anti-de Sitter space, that you could have different kinds of boundary conditions. It's kind of up to you how to choose the boundary conditions. You can choose their Dirichlet-like or Neumann-like boundary condition. There are different things you can do, and there's a lot of discussion of that in the literature. But here, I guess I'll start on a new board here. we want to talk about boundary conditions at scri plus or scri minus. And there you wouldn't think that you would have the same freedom of choosing what the boundary conditions are. Indeed, you would like to start with some. Now, Arnowit, Deser, and Misner were looking at boundary conditions at spatial infinity on a space-like slice. And there you would have some choice. If you want to study finite energy momentum configurations, you impose that things fall off in a certain way. It's a free world, and if you'd wanted to, you could have discussed configurations with infinite energy and so on, and there is some discussion of that. It's not such a useful thing to think about. But once you have some smooth initial data here, it's going to do whatever it does at null infinity, and you can't just arbitrarily impose boundary conditions up there. Now, what would we think it does? Well, we'd like the energy. So the energy flux in electromagnetic radiation, that should go, if we take a sphere here, its volume is of order r squared. So in order for the energy flux at any moment, I'm not talking about the integrated energy flux, but energy at any moment, which is a weaker thing, in order for that to be finite, TUU should go like 1 over r squared. But TUU is equal to FUZ bar 1 over r squared gamma ZZ bar. Now, what is this 1 over r squared doing here? Well, that's because we defined our metric to be ds squared is minus du squared minus 2 du dr plus 2 r squared gamma ZZ bar dz bar. So when we invert this, the metric on the sphere, we get a 1 over r squared there. So that suggests that we want FUZ to be of order 1. On the other hand, FUR is the long-range electric field. And so we'd like that to go like 1 over r squared. And similarly, FRZ should also go like, is that what I took? Yeah, FRZ should also go like 1 over r squared. Right, because why is that the right behavior? I guess that's the magnetic. Yeah, that's the, wait. Yeah, that's the, okay, I don't remember why that's the right behavior now. Okay, but anyway, that's what you want.
FUR is finite because you want electric charge to be?
Well, electric field will fall off like 1 over r squared. So the energy would go.
For static electric.
GRR is of order 1. So there's another term here that goes like plus FUR. So right, so that would say 1 over r. But okay, the long-range if we have an electric field going like, don't make me work it out now. If we have a long-range electric field which is going like 1 over r, the energy will be infinite. And the charge will be infinite. Yeah. Yeah. Yeah, just by Gauss law. Okay, so all right. So this says that we want AZ to be of, we can take AZ of order 1 consistently with this. We can take AU to be of order 1 over R, and AR to be of order 1 over R squared. So if we tried to have any stronger boundary conditions with A, we would clearly violate this. We would not be able to. It would be too strong, right? If we make it too strong, then we say that we're disallowing some initial data, and we want to allow all reasonable initial data. So now we ask the question, what kind of gauge transformations does this allow? Well, this allows, so we have delta AZ equals dz epsilon. Delta AU is equal to du epsilon. And delta AR is equal to dr epsilon. And that's consistent with, these boundary conditions are consistent with epsilon equals epsilon, an arbitrary function of zz bar, plus order 1 over R corrections. So already this very simple analysis, so in du, so du, I can't let this epsilon be depend on u, because then I would violate this boundary condition here. So already this simple analysis suggests the result, which we came across in a much more complicated way, namely that the non-trivial large gauge transformations are generated by functions epsilon, which depend on z and z bar, and not on u. Okay. So right. So this is another way of thinking about where these asymptotic symmetries come from. Now, the thing that is a little hard to answer in this way of looking at it, what I did was the most natural, simple, and obvious thing. And it's usually the case that the most natural, simple, and obvious thing turns out to be correct. But if you start to think about it, usually, but not always, if you start to think about it a little harder, you might ask, why couldn't I have allowed AU to have, I could have maintained these conditions by AUs that were pure gauge. This doesn't exactly imply this. This is consistent with this. I can't go any stronger than this. But this doesn't exactly imply this. And so you might have asked, why couldn't I have relaxed this boundary condition on U to allow it to have an order 1 piece, which was the U derivative of something? And the answer is I could have. But then after a long analysis, I would have eventually found what we found earlier, that the differences between that the charge in the end depends only on the value of epsilon down here, and the different charges where epsilon depends on u in a different way, all the difference between them acts trivially. Okay, so that's another very useful, though less rigorous way of thinking about things. Any questions? Yeah, I think Scott was, or somebody was asking me earlier, why couldn't I, I started out with my charges constructed down here. Why did I make them constant up here? And, you don't learn anything extra by doing that because the charge only depends. Those two charges would be equal. The charge that would generate a asymptotic symmetry that differs from this only by some u-dependent piece, something where you start, if you have two epsilons which take the same value at scribe plus minus but differ elsewhere, the associated charges would be equal. And that would come back to here. They would be trivial. The difference between the two things would be trivial. The charge would always vanish. So in order to learn that from here, I would have to go through the whole story of constructing the charges. And there's another example, of course, of this asymptotic symmetry group analysis. ADM did the spatial infinity, and then BMS did null infinity. But they were never able to construct, they were not able to construct the charges. They never succeeded in constructing the charges. And so there were various other, there was the Newman-Unti group, and there were variations on BMS. The simplest idea, they got it right, but we now know they got it right, but there were contenders along the way of other groups, the Newman-Unti group and so on, and so forth, and you couldn't tell which the real group was without doing more work. So this is the quick and dirty way to do things, which is usually good, but sometimes there are subtleties arise which can only be resolved by more careful analysis. All right. So any questions about that? All right. So now we're going to go back. Let me review some of the things that we talked about last time and some definitions. So the first definition is if we take the zero mode of the radiative component of the electromagnetic field with respect to retarded time, and given that AU has no constant piece at infinity, this is just DZAU, a DUAZ. So I can write this as the leading component of AZ, the difference between its value at the top of scribe plus and its value, at the bottom of scribe plus. And I defined that to be E squared dz times some function n. I showed that using the Bianchi identity that this was always the gradient of a real function. And I, for convenience, threw an E squared in there. So this field n, this is the zero mode of the gauge field. I call it the soft photon, even though that's really sort of quantum language. This is a classical object. It creates a soft photon. And I'm characterizing it by this field n. And this is on scribe plus, and there's something similar on scribe minus. Then there was another component of A0 that was important. A0 can be written as a piece A hat, which, so this is A0 everywhere, not just at the boundary, and it can be decomposed in terms of a piece A hat, which has a Fourier transform. The full A0 in general doesn't have a Fourier transform, plus a constant, which I called C, that is a constant with respect to U. So that this is basically half. This n is the difference of A at the two ends of scry, and C is the sum of A at the two ends of scry. And then we computed a symplectic form, and we found that the symplectic form paired it paired the kind of radiative part of the gauge field on scry, the part that has a Fourier transform, the A hat part, with itself, and then it paired this soft photon field with its conjugate C, which is the constant part of A. Okay, so using this symplectic form, we showed that Q plus epsilon, which was 1 over E squared, the integral scry plus minus of epsilon star f, has the property that Q plus epsilon with AZ so it generated a gauge transformation. And now, Andrew asked me a question about this. So these equations here are really, I'm doing a classical analysis here. And so I could be talking here about Dirac brackets. And then I wouldn't have the I here. But I don't want to put in I's later. So, I don't want to, like, at some point, that's too confusing. So what these really are semi-classical quantum brackets. And I don't, at this point, one could try to see if these equations have loop corrections. But that would entail understanding in this language how to do loop corrections where your basic variables are fields on scry. Nobody's really ever worked that out. So instead, what we're going to do is we're going to rewrite these things in terms of not fields on scry, but plane wave fields. That's the asymptotic plane wave scattering states. And then we can use the 100 years of development of quantum electrodynamics to we don't want to redo that in a different notation. We can use all that to investigate the question of loop corrections. Okay. So then we said, OK, it's a symmetry. So we have a Ward identity, Q plus epsilon S minus S Q minus epsilon. This is, outstate, any outstate, any instate is equal to 0. And we worked that all out. And we found a formula, which we're going to come back to later today, which is that this can be rewritten as minus 2 d squared z dz bar epsilon dz out n, which depends on z and z bar, s minus s n minus in, where this n minus, I suppose logically I should have a plus here because this is unscribed plus, but it gets cumbersome to carry that around. So the n minus denotes the field unscribed minus constructed from in operators, is equal to the sum from k equals 1 to m over incoming particles. So we assume that we had some set of incoming particles of charges qk, and then epsilon zk in evaluated at the point on the sphere. These are incoming charged massless particles. We're going to allow them to have mass a little bit later. So we have the incoming charges weighted by the value of the gauge parameter at the angle they're coming in from, and then minus k equals 1 to n of the outgoing charges, epsilon zk out, z bar k out. And then that is all times the same S matrix element without any soft photon insertions. Okay, so charge conservation in a situation where we have m incoming and n outgoing charged particles, charge conservation, this infinity of charge conservation law implies this infinity of Ward identities. Okay, so now we want to proceed to rewrite this in terms of, usually when one talks about S matrix elements, one works in a plane wave basis. So we want to understand what this formula means in a plane wave basis. And towards that end, in a problem set, you showed that AZ0 U ZZ bar, this is a field on Scri plus, can be written as minus I over 8 pi squared square root of 2 E over 1 plus ZZ bar integral from 0 to infinity d omega q A dagger out positive helicity omega q x hat e to the minus I omega q u.
There's no dagger at the end.
Oh, sorry, that was the plus. Yeah. Sorry. Minus a minus out dagger omega q x hat dagger e to the I omega q u. And here I have z and z bar, and here I have x hat. And the relationship between them we wrote before is that, well, we wrote it for the x's, which differ from the vector x, which differ from x hat by a factor of r. But we have x hat 1 plus I x hat 2 is equal to 2z over 1 plus zz bar. And x hat 3 is equal to 1 minus zz bar over 1 plus zz bar. So let me just pause a moment here because we're going to be going. So if we have a unit vector, squares to 1, that can be viewed as a coordinate on the sphere. Here is the explicit relationship between the components of that unit vector and z. So we'll be going back and forth between z's and x hats and q hat and so on. Okay. So that is how this side is a function of z. You pick a point on z on the sphere. That gives you an x hat. And then we have a creation or annihilation operator, which creates or annihilates a photon with pointing in that direction. All right. Now, where am I? Okay. So now we need to we want to write this. So here is the basic relationship, right? This creates a familiar plane wave object. And so this is the dictionary from the objects, from the operators at Scry to the familiar Weinberg, Bjorkanen, Drell, Schwartz plane wave operators. Okay, so, but this thing involves this n. So what is n? We need to know what n is. In fact, we don't need to know what n is. We only need to know what dzn is. So let me write dzn. Well, dzn, well, it's over there, but we need to be a little bit careful about the zero momentum limit. So let's write it as equal to 1 over t2e squared. The limit as omega goes to 0 from above. Actually, I don't need to say from above because it doesn't matter the way I've written it. Du e to the I omega u plus e to the minus I omega u F0 uz. And we need to do it this way because we want something which, well, of course, this is not going to be Hermitian because we've got dz here. But if we add dz bar, that should give us Hermitian. And if we were to just take one of these, e to the I omega u, and take the omega goes to 0 limit, we would get something else which wouldn't be a Hermitian operator. Okay, so we're taking the limit in this way. And that is equal to minus 1 over 8 pi e square root of 2 over 1 plus zz bar, the limit as omega goes to 0, plus, now let me write it, of omega a plus out omega x hat plus omega a minus out omega x hat dagger. Now, the first thing you might say when you see this is, well, why do we care about this operator? We're taking the limit of omega goes to 0 and multiplying by omega. You might think it's just uninteresting. It's just 0. But if that thing were 0, this equation would sure make no sense because it would tell us that the right-hand side had to be 0 all on its own. And the way that all reconciles itself is that these things have pole. These A daggers, their S matrix elements, have poles in them, which cancels the explicit omega I put in here. Okay, and then there's a similar formula for dzn minus, which is blah, blah, blah. And it's the same, except it has things like a in minus omega x hat dagger. I'm not going to write it out. Okay, So now we have defined this guy. And okay, now I want to take that ward identity in the box there, and it's true for any epsilon. But let me consider a special epsilon, which is just equal to 1 over z minus w for some z. Did I write it in? Ooh, I wrote. Wait, I guess. I wrote that guy in terms of. Okay, I have a little notational conflict here. Let's do this. It's 1 over z minus w. And then I need to use the fact that dz bar of 1 over z minus w is equal to 2 pi delta squared z minus w. So if I do that, that dz bar epsilon just gives me a delta function, and I just get a local expression on the top, unintegrated. I can easily integrate over z using the delta function. And then I have to take the epsilons that I've written there on the right-hand side and replace them with 1 over z minus whatever it is. And if I were to do it this way, I would get an expression that depends on w. But I'm going to change w to z. So what I get is that I can now rewrite the box as the limit as omega goes to 0 plus of omega out a dagger out of omega x hat s minus s, not a dagger out, a plus out, minus s, a minus in dagger, omega x hat in. That's what the top thing collapses to. I'm also substituting in with the expression for dzn and dzn minus, which I didn't explicitly write out there. And that becomes equal to square root of 2e times 1 plus zz bar times the sum k equals 1 to n qk out over z minus zk out minus the sum from k equals 1 to m over incoming particles q in k over z minus z k in. Sorry?
Should that be omega x hat dagger in the
The argument?
Yeah.
X hat is real. X hat is a real three-dimensional vector. So x1 plus, it's a vector in R3 that is a point on the unit 2 sphere. Z is complex, but x hat 1, but its real and imaginary part are related to. That dagger went on that guy. I wasn't trying to write this expression carefully. Okay, a little times, of course, out, S, in. Now, a little teaser for 2 or 3 weeks from now. This looks like a word identity of a current algebra on a sphere. When you insert in a two-dimensional conformal field theory, when you insert a current, we can think of Z as a coordinate. Z is a coordinate on a sphere. We insert a current, and you have some correlation functions, a Kac-Moody current, and their operators of charge Q. You get exactly this kind of word identity in a current algebra. And indeed, this is all isomorphic to some word identity of a current algebra in a two-dimensional field theory on a sphere. And we'll come to that in a few weeks. Okay. Now I want to compare this. So now, in principle, I could go to here and get rid of all the z's and write them in terms of momenta of the particles, but I'm going to do it in a slightly different formula, certainly different way. That's just somehow a little awkward to work it that way, even though it is possible to go both backwards and forwards. What I'm going to do now is I'm just going to write down the textbook formula for the soft photon theorem. I'm going to show that it's equivalent to this by going from plane waves to Z rather than from Z's to plane waves. It's less writing. And then, after that, I'm going to review the standard textbook derivation of the soft photon formula. Okay, so the standard soft theorem, which was first written down by Francis Lowe in 1958, but the way we think about it now appears in a paper by Weinberg. What, you want to say Bloch and Nordsick or something? Okay, well, I would say they don't care about references, but Francis Lowe isn't a I don't know. I mean, it evolved, right? I mean, in some you could also credit it to Maxwell. I don't know. It had more and more it had more and more, developments. I mean, Bloch and Nordsick was before QED, so I don't. But interestingly enough, I don't think Lowe really used Feynman diagrams. He used some kind of dispersion theory. So the modern way that we think of it in terms of Feynman diagrams is due to Weinberg. And by the way, those other people also, they had something which was equivalent, but it involved both incoming and outgoing photons. And I think Weinberg was the first one to talk about just one photon. All right, so what he writes is that the limit as omega goes to 0 plus of omega out a plus, okay, so there's going to be no z's here. This is standard quantum field theory formula. A plus out of q. So we're using q for, I'm going to tend to use q always for the momentum of the photon or whatever the soft particle is going to be. S in is equal to the electric charge times the limit as omega goes to 0 plus of the sum from k equals 1 to m, qk out, pk out, contracted with the polarization of the outgoing photon, which in this case I've taken to be positive helicity, so I should put epsilon plus there, divided by pk out dot q minus the sum from k equals 1 to n, and there's an omega here. Omega qk in pk in dot epsilon plus over pk in dot q. And that is equal to times, keep forgetting this, I want to write it here, out S in, excuse me for squeezing, because I want to fit another line in here. And that's equal to minus the limit as omega goes to 0 plus of omega out S A in minus dagger Q in. Okay. So first of all, this isn't quite how it's usually written because I've multiplied both sides of the equation by omega. But so there's an omega here, omega here, omega here, and omega here. So usually Weinberg didn't write that omega, and what he said, now notice that omega, so Q will be omega Q. So in the limit where Q goes to 0, the soft limit, omega goes to 0, this ratio is finite. In other words, the size of Q, the length of Q, if you like, or Q0, doesn't appear in this expression. It factors out. It only depends on the direction of Q when you write it this way. So what usually would have been said would to write the formula without the omega, and then there's a pole as Q goes to 0. That's called the soft pole. There's another pole. So now we're about to compare these expressions. Sorry, I should say something I needed to define. If I write here, then I'm in trouble. as before, I'm taking my in state to be of the form Q1 in, P1 in, dot, 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 Qn in, Pn in. That's what the Q's and P's are here. And yeah, so now notice also that there's, in addition to the Q goes to 0 pole, if I hadn't just multiplied everything by omega to hand, there's a collinear pole here. In other words, since Q is a null vector, and I'm taking P also to be a null vector, when P is proportional to Q, this goes to 0, and this formula diverges. And we see that up here, too, because Z is the location of x hat and Z are related by this formula over here. So Z is the location of the outgoing photon, the point on the asymptotic sphere that the photon pierces. And whenever any one of the particles is going to, Zk is equal, when any of the Zk is equal to P, then I get a pole there. So the pole structure of these two expressions is agreeing. And now there's another part of the Weinberg formula here, which is that these two things are equal. In other words, up to a sign, if you annihilate an outgoing positive helicity photon, you get the same thing as creating an incoming negative helicity, creating an incoming positive helicity photon. So did I really want to? Okay, so these two terms become equal. All right, now what do we do now? Okay, so now what we have to do is, it's easier somehow to turn this expression into that one than it is to turn that expression into this one. And because we have a very nice explicit formula, I mean, both things are possible. But we can write P in K mu. This is a formula we saw before. We can write it in terms of E in K times 1, and then Zk in plus Z bar K in. So this is P0, P1, P2, P3. 1 plus Zk in Z bar K in. And then P2 is the same thing with an I and the imaginary part of Zk. And finally, P3 is the same thing with a 1 minus Z bar squared. In other words, if we know that the photon is going to land at the point Zk, or sorry, the massless charged particle is going to land at the point Zk, then this is what its momentum must be. And similarly, we can do this. Well, we already wrote down the formula for this expansion for Q. It looks exactly the same, except with Z, K, with E in K replaced by omega, and Z, K in replaced by Z, and similarly for the P outs. And then, if we do that, all these P's will disappear. Notice that the E's will cancel. And if we go, well, we do all this, it's some algebra. I'm not going to do it on the board. But what we find, oh, and then we get to take the difference of these, we get to add these two terms and multiply by 2 to make it look like what's up there. And so with all these substitutions, this formula, the standard soft photon theorem in its standard plane wave form, reduces to the Ward identity that we derive from invariance, Ward identity that we derive from invariance under large gauge symmetries, or equivalently, the matrix element of the charge conservation law. Okay, so this establishes, in a minute, I'm going to go, actually, we'll take our 5-minute break, but in a minute, I'm going to talk about how you get this formula out of Feynman diagrams, but this is kind of a central result. We've connected the low Weinberg soft theorem with this story about infinite number of conservation laws. So let me pause there for any questions. Yes? I mean, oh, okay, so I took a special form of epsilon, and that was a trick to make this formula is true for any epsilon, but it's not very hard to show that if it's true for that special form of epsilon, for any w, I substitute epsilon as 1 over z minus w. If that is true for any w, then it's just a few lines to show that it's true for any epsilon. So effectively, taking epsilon equals 1 over z minus w is equivalent to taking an arbitrary function. Yeah. Yeah, that's a plus. Is that what you're asking me? That's right.
Kind of a verification.
It's just tedious algebra.
Oh, okay.
I could make you do it on a homework set if you insist. But I think what I tried to sketch the plausibility of this working, right? Because we saw that the E's canceled. We saw that the poles were in the right place. You can see the general feature, that the general features work out without checking all the details. Okay, let's take 5 minutes and then reconvene. Okay. So the next order of business is to give to talk about the field theory derivation of this theorem here in the form given by Weinberg. And so I've been, up until now, I've, with the field equations, and there's been a lot of, I've been careful about stating what my conventions are, and taking care of all the factors of 2 and pi. And of course, it's important that all those factors have matched perfectly here. And now I'm going to talk about a Feynman diagram derivation of the soft theorem. And it's a couple lectures just to spell out your conventions for Feynman diagrams. I don't want to do that. So I am just going to write down formulas that are true in a standard set. The 2's and the pi's and so on are correct in some standard set of conventions. And in the various papers on the subject, that's all spelled out. But I don't want to spend a lot of time on factors in Feynman diagrams now. So what is the basic idea? Well, the basic idea is, what does this formula say? And in fact, in Feynman diagram derivation, one derives it. Let me erase the omegas here. This is the form that you'll find it in. And perhaps one would write it without this limit here and just state that this is plus, this is a pole in Q, and this is a statement which is that this matrix element is equal to the original matrix element plus corrections which are of order Q. So the pole is the leading term. That's the way it's usually thought about in Feynman diagram language. So the statement is this. Let's take any scattering process with some incoming and some outgoing particles. And then let's add to it one outgoing photon, which I'll denote by a wavy line, with momentum q. So this has momentum p1 in, ... pn in, and then we have p1 out, ... pn out. I've only drawn 2 in and 3 out, but there can be more. And then we add another outgoing photon with momentum, another outgoing particle. So in fact, I'm just going to derive this one for an outgoing photon. And the ingoing case is similar. And now we want to compute a new scattering amplitude, but only in the soft limit. We're only interested in the soft limit. So I can write that as a sum of terms. There's 2 kinds of terms. And so that photon could attach to an external line like this, or it could attach to an internal line, and it could attach to any one of the n plus m external lines. So it's terms like this, where I attach to all possible external lines, and then it's terms like this, where I attach somewhere to an internal line in the Feynman diagram. And this, of course, is equal to a sum of an infinite number of terms whose detailed form depends on what, I haven't even said now what theory I'm talking about, except that we have a photon. That's one of the beauty of this thing, is it applies to every theory that has a photon in it. Okay, so in this 5-particle scattering process, there would be plus 4 more terms like this. Now, how do we think about this? Well, the rule for computing Feynman diagrams is you start out by computing the Green's functions, the time-ordered products, and then using the Feynman I epsilon prescription, and then you amputate the internal legs. So Feynman diagrams, of course, we have rules for vertices, and in particular, we have rules for the photon propagator. And so what happens when I add the extra photon is, since this part and this propagator and this propagator are amputated according to the LSC reduction procedure, all I'm doing is adding this propagator here and this vertex here. Right? So the difference between this diagram and the diagram without the external photon is just this propagator here and this propagator here. So now I have to say a little bit about what the interaction is. Well, let me take the interaction to be equal to the interaction, which is linear in a photon. It's equal to the gauge field AA contracted with the current JA. And for a scalar field of charge Q, JA in our conventions, where the E's are all in, I've taken the factors of the electromagnetic coupling E, and I've put them all into the F squared, minus 1 over E squared. So there are no E's in the interactions here. So I have I, Q, phi, dA, phi star, minus phi star, dA phi. And for a plane wave, this is just 2, and the 2 comes from our normalization in some conventions of the single particle states. For a plane wave, this will just be 2q PA. This is the electromagnetic current associated with, for a charge Q scalar field phi, meaning under gauge transformations it goes like e to the iq epsilon. And moreover, epsilon, we want to take the polarization of the photon epsilon to obey epsilon A QA equals 0, where Q is this momentum. So, okay. So if this has, let's say this has momentum Q, and this has momentum P. So now we need to work out the two factors. And so what will we get? Well, first of all, we have this propagator here. And the propagator there gives us a factor of minus I. So we're taking a particle of mass m. So unlike in the discussion, this is also another interesting feature. When you prove that, so far we've only proven this. Later on, we're going to generalize to the case of massive particles. And the proof is qualitatively different for massive, in this asymptotic description. It's qualitatively different for massive and massless particles. But in the standard proofs of the soft theorem, they were actually mostly interested in the massive particle case. But it hardly matters at all. I mean, it doesn't even really, the mass doesn't even really appear. So we have p squared equals m squared. And for a massive particle, and we could be taking m squared equals 0 here. And so then this propagator here, the extra thing that we're taking, in some conventions, this momentum here is going to be p plus q. That's true in any convention. But in some conventions, the propagator is minus I over p plus q squared minus m squared. That's the propagator for a scalar field. But that, of course, is equal to minus I over p squared plus 2p dot q plus q squared minus m squared. Just expanding the square. But q squared is 0. It's a photon. This is an on-shell scattering amplitude. So all these external lines have to be on-shell. So q squared is 0. P squared is equal to m squared. And so this just becomes equal to minus I p dot q, 2p dot q. That's the propagator factor. What is the vertex factor? Well, first of all, I get a factor of E from the fact that my mode expansion in terms of normalizable one-particle states in the formula that you derived in the homework, there's an E in front of it. In more standard conventions where there are no E's in propagators, there would be an explicit E in the interaction. But OK, it's invariant under field redefinitions. So we have E. And then A, of course, is proportional. AA is proportional to polarization, epsilon A. So we get epsilon A contracted with JA, which is 2QPA. So that is the vertex factor. And there's also an I at the vertex. This is e to the I s interaction. And so I now take this, multiply by that. The 2's cancel. And there was a Q there from the J. So I just get E Q epsilon dot P over P dot Q. The i's multiplied to 1 and the 2's cancel. That was supposed to be my big Q. Yeah, OK. OK, so but now I can take this and obviously I get one such term for every outgoing particle. So I have the sum from k equals 1 to m pk qk dot q. Now, and then for the incoming particles, there's a minus sign, and I get k equals 1 to n of e qk epsilon dot pk over pk dot q. And these are out, and these are in. Okay, so at the end of the day, if I just consider these diagrams, all I do is multiply the S matrix element by this funny factor, which you may recognize as the same, sometimes called the soft factor, which you may recognize as the same thing that I've written over here. Now, I haven't included everything because what about these extra terms here? Well, the point there is that the internal propagators are never on shell. They never have p squared equals m squared. So I don't have this cancellation here. And if I take q to 0, the difference between p squared and m squared will dominate, and I won't get a pole. So these diagrams are most certainly non-zero, but they don't contribute to the pole. So I can just forget about this. So that is an extremely simple derivation, and it up to some signs, you get the same thing if you have a soft incoming photon of the same formula. Now, so any questions about that? Now, an important feature here of this formula, which has provided some alternate derivations of it from the Feynman diagram point of view, or in this form, is that we would like this defines the polarization vector only up to shifts of epsilon by q, because q itself is 0. So the physical scattering amplitude with a soft photon should not depend should be invariant if we shift epsilon by any multiple of q. So it's interesting to look at what happens to this soft factor. Well, if we shift this by q, if we shift epsilon by q, this p dot q cancels this p dot q, and we just get that it equals the sum over k e times qk out, this had an out on it, minus the sum over k e qk in. In other words, charge conservation, global charge conservation, guarantees that this soft factor is gauge invariant. And that can be used to, or that was used, I think really that was part of how Lowe argued for this, Francis Lowe argued for this formula in 1958. Okay, now I've only worked it out here for a scalar, for the case of a scalar. If you do a fermion or some other kind of charged particle, it's a little more complicated, but it works out to be the same thing. And the fact that it has to work out to be the same thing in this language, I mean, it's some work to do it. I don't think Weinberg did it in his original paper, but the fact that it has to be worked out to be the same thing can be seen. One way of seeing it is from the fact that this is the only formula that is invariant with the right dimensions and so on, that is invariant under these shifts of Q, shifts of epsilon by Q. Okay, any questions about that? Okay, so now mostly I'm deferring the discussion of gravity, but this is so short and simple that while I've got this on the board, I'm also going to, as Weinberg did in his original paper, derive the soft graviton theorem. So I don't need to rewrite these diagrams, but because I can just say that this is a graviton of momentum q instead of a photon of momentum q. And then I need to know what the interaction is. So let me write the interaction as S interaction is equal to a half kappa HAB TAB, where for a scalar field, TAB, this is how the graviton field, which is replacing the photon, HAB, and here this field is normalized so that there's no kappas. So kappa is the square root of 32 pi times Newton's constant g. And this field is normalized so that there's no factors of Newton's constant or kappa in its kinetic term. Then the interaction vertex becomes like this, where TAB is just equal to dA phi dB phi minus a half GAB d phi squared. And I have a graviton with polarization so that HAB, it has momentum q, and it has polarization epsilon AB, and epsilon AB QB is equal to 0. That generalizes this formula. And now I have the same argument that I need to multiply the propagator. So the propagator contribution is exactly the same. The extra propagator that you get is exactly the same whether you have an external photon or external graviton. And so I get a minus I over 2 p dot q. And so these 1 over p dot q, these poles, which become these holomorphic poles when we go to momentum space, are ubiquitous in these soft theorems, whatever kind of soft theorem we're discussing. But now I have to have something different on the top because I have a different interaction term. And so what does this interaction give me? Well, this thing here just becomes 2 PA PB. And the GAB won't contribute because this should also be traceless. And yeah, I didn't write that down. Transverse and traceless, epsilon AB, 8AB is equal to 0, or GAB. And so I get a kappa, an explicit kappa. And I get PA, PB. I guess this 2 cancels the 1/2. And then I get HAB proportional to epsilon AB. And then I get an I, which cancels this minus I. And so what I get finally is kappa over 2 epsilon AB PA PB. And again, if I had in and out particles, I would have a sum over out minus a sum over in. Of PA, I can't write it that way. So this is just for one particle. So more generally, if I have n incoming, n outgoing, m incoming particles, I get a saw factor, which is kappa over 2 sum k equals 1 to n pk out a pk out b epsilon ab. This factor is the coupling of the minus a similar term for in, the coupling of the graviton to the stress energy of the particle, and divided by pk out dot q. So I get a very similar looking formula where epsilon pp replaces epsilon, in the gravity case, replaces epsilon p in the gauge theory case. And just like in the gauge theory case, I also can't get poles by coupling to internal lines. Okay. All right. So my next subject, which I don't think I want to start with 5 minutes left, is to go back and understand from the asymptotic point of view what we should do when we have massive particles. But let me just pause now and see if there are any questions. Oh, sorry, one more thing I wanted to say about this. Again, what happens if we shift? We should be able to shift epsilon by epsilon AB goes to lambda A, any function of Q, times QB. That would be gauge invariance in the gravity case. And again, if we do that, we can pull the lambda out front, and we get pk. Let's shift this guy. So this pk dot q shifts, cancels with that pk dot q, and the whole thing becomes lambda a contracted with the sum over out. Sorry. So the whole thing, if I shift by q, I have this lambda a, the sum of p over k pk out minus the sum over k pk in sub a sub a. The p dot q's cancel. Now, this is just overall energy, momentum conservation. So again, the consistency and gauge invariance. So we saw that the consistency and gauge invariance of the soft photon theorem and the particular form of the soft factor was required by gauge invariance. Well, gauge invariance and together with charge conservation, of course they're related, two sides of the same coin, implied the consistency of this formula. And here we see that energy momentum conservation, global energy momentum conservation, is required for, implies the consistency of the soft photon theorem. And there's also, to answer somebody's question about superrotations, there's also angular momentum conservation. And there's another soft theorem that we'll talk about later that is related to global angular momentum conservation. So, any questions? Yes? Yes, this also looks like a ward identity in a Carl CFT, and the one that is related to superrotations, and is this stress tensor, the ward identity for the stress energy tensor in a Carl CFT. But those statements haven't been as fully investigated as the one for the U1. More questions? Okay.